Welcome to part 2 of the fundamental theorem of line integrals. Let's start with a quick review of the theorem and then we'll take a look at an additional example. The fundamental theorem of line integrals states that if the vector field f is conservative, meaning it's equal to the gradient of little f, then the line integral between any 2 points is equal to the difference in the value of the potential function, as we see here, at the ending and beginning point of the curve. So we first have to verify that the given vector field is conservative, and then if it is, and it satisfies the conditions listed here, we then need to determine the potential function, and then we can evaluate the line integral. So let's look at our example. Here we have a vector field in R3, and if we want to use the fundamental theorem of line integrals to evaluate this, we first have to check to make sure that this vector field is conservative. Remember, it's conservative if the curl of f is equal to 0. So the first row would be ijk. The second row would be from del, or the partial derivative operator. The third row is from the components of vector field f. So here's our 3x3 determinant, but to evaluate this, I'm going to go ahead and use the diagonal method. So I'm going to copy column 1 and column 2 to the right. So we'll add the products of the blue diagonals, and then we'll subtract the products of the green diagonals. So the partial derivative of x squared e to the z with respect to y, that would be 0, plus the partial derivative of 2x e to the z with respect to z, that'll give us 2x e to the z, plus the partial derivative of cosine y with respect to x, that would be 0, minus the product of the green diagonal. So here we'll have the partial derivative of 2x e to the z with respect to y, that's going to be 0. Here we'll have the partial derivative of cosine y with respect to z, that's also going to be 0. And then here we have the partial derivative of x squared e to the z with respect to x, that's going to be 2x e to the z. So the curl is equal to 0, which tells us that the vector field is conservative. So now we can use the fundamental theorem of line integrals to evaluate this as long as we can determine the potential function. So let's go ahead and do that on the next page. Remember, if the vector field f is conservative, it's equal to the gradient of little f, which tells us that the components of vector field f are equal to the partial derivative of f with respect to x, with respect to y, and with respect to z. And so if we can determine the original function f of x, y, z, we can use that to determine the value of this line integral. So I'll have to integrate the x component of vector f with respect to x. We'll have to integrate the y component with respect to y, and then integrate the z component with respect to z, compare the results to determine the potential function. So here we're going to have 2 times x squared over 2, that'll just be x squared e to the z. But now we're only recovering the x part of the potential function, so our constant of integration could be a function of y and z. Integrating cosine y with respect to y, that's going to give us sine y, plus a possible function in terms of x and z. Integrating x squared e to the z with respect to z would just give us x squared e to the z, plus a possible function in terms of x and y. Now by comparing these 3 results, we should be able to come up with the potential function f of x, y, z. Notice Notice that x squared e to the z occurs twice, so we'll only include that once. That'd be x squared e to the z. We also have to include sine y, and then our constant of integration will be plus c. But notice when applying the fundamental theorem of line integrals, the c would simplify out, so we won't include it when we use our theorem. Now that we have our potential function, we were given that the curve c is from the point 1 pi over 2 0 to the point 3 pi natural log 4, we can determine the value of this line integral. It's going to be equal to the potential function evaluated at 3 pi natural log 4 minus the potential function evaluated at 1 pi over 2 and 0. Let's see what we get. We'd have 3 squared e to the natural log 4 plus sine of pi minus 1 squared e to the 0 plus sine of pi over 2. Well, 3 squared is equal to 9. E raised to the power of natural log 4 is equal to 4, plus the sine of pi is going to be equal to 0, minus 1 squared is 1, e to the 0 is 1, so we have 1, plus sine of pi over 2 is also equal to 1. So we have 36 minus 2, which gives us 34. And that'll do it for this video. Thank you for watching.